of the Technology Committee, José Ferrari Careto, for the welcoming. José, you're still muted.
Okay. Hello. Good morning. Welcome to this seminar regarding flexibility. So the Go4Flex. I believe that you'll find this seminar very interesting, as we will be here discussing a very hot topic regarding energy distribution. Nowadays, flexibility is in the middle of the main discussions regarding the sector, and I believe that we'll benefit from the discussion between different people from different countries, and based on a report that was done by colleagues from different geographies, from different companies, uniting, putting together their knowledge and their thinking about this very important subject. I think that this is one of the things we do better at EDSO, which is to reunite knowledge and to foster discussion among different people from with different backgrounds, from different geographies, with different technical experiences, coming from different markets. And I think that the result is very clear in this report. If we look to the quality of the report, so I think that we can be very optimistic about the future of flexibility and the future of knowledge sharing at EDSO. Regarding flexibility, I believe that there are a lot of expectations regarding this topic. I know that from the political point of view, from the regulatory point of view, there are a lot of expectations regarding this. I think that aside or out of the technical discussions, I believe that politicians and regulators, I think that they put a lot of hope in flexibility in order to solve some problems that we face nowadays. Some of them are related with the need of investment, the huge investment we need to do in our networks. And I believe that there are a lot of people thinking that we can replace part of that investment with flexibility. So I think that the expectations are very high, which means that we need to discuss this very carefully, and we need to understand what are the technical consequences of the flexibility adoption. And above all, I would say how material flexibility can be in order to solve the challenges or to overcome the challenges we have ahead. I believe that this will be part of the discussion today. Having said that, we know that when we are talking about flexibility, we are talking about different dimensions of flexibility, and the report states three areas where flexibility can be used. So the flexibility for local congestion management, the flexibility for voltage control, and the flexibility for grid development plan. I would say that each one of those areas are a specific subject by itself. So they are very different. And I believe that the autonomy of each DSO regarding these three dimensions, the autonomy is very different. So if we are talking about flexibility for voltage control is one thing, and if we are talking about flexibility for local congestion management is another thing, as the autonomy we have, the dependency we have vis-a-vis the market is different in each one of the dimensions. So I think that this increases also the complexity of the subject, the complexity of the flexibility. And on top of that complexity, I would say that flexibility doesn't go alone, meaning that we need to put together a lot of observability dimensions regarding our networks in order to leverage flexibility. So a very complex topic, a topic where expectations are very, very high, a topic where technical challenges are also high, and a topic where we DSOs can't walk alone, as we depend a lot on regulators, we depend a lot on markets, and we depend a lot of on the technical aspects of flexibility. So I believe that this will be a very rich debate, a very rich workshop. I know that we will have a period of Q&A, and please use it, because I believe that we'll have a lot of doubts as we are in the beginning of this road of flexibility, and I think that we can all benefit of discussing the subject on a very open way, with participation of very different people from a lot of different countries. So enjoy, and I hope you have a very good session. Thank you very much.
Thank you, Jose. So jumping for the workshop itself, and going quickly through the agenda of what we have prepared for you today, we will start with a theoretical overview of the Go4Flex report, presented by the leaders of this report, Eva and Juan. And then we'll go through the 5 use cases that are also presented on the report. And then we will have, as I said to you, a round table where we will put the questions that you can add here below on the Q&A tool. And then we have the final presentation from our speakers with the last word of on the report and the work that needs to come next. So now I give the stage to Eva and Juan for the theoretical overview of the Go4Flex report.
Okay, thank you very much. My name is Ewa Mataczyńska. I work for PGE Dystrybucja. This is the largest distribution system operator from Poland. And I work at the grid development and modeling department as head of grid operational modeling office. So Juan, could you please...
Hello, yes, I'm Juan Martí. For sure, I have been in Iberdrola working for 30 years with ADMS systems in several countries. So probably many of the audience already know me in some of the events. So that is me, please.
Okay, so thank you. The first part of the workshop is theoretical overview of the report. And so could you next slide, please? Yes, so the report was prepared as part of the work of ETSO task force #1, that is active network management. This is the second report prepared by this task force. However, the previous one is only for internal needs. This one is available on the website of ETSO, so you can download it and read this report. This is the report contains of more than 80 pages. So during today's webinar, we are not able to present all details. That is why just only general overview of theoretical part of the report will be presented. So next slide, please. Let me start from the definitions, how we understand the flexibility in the report, because it is important part of the report to underline how we see this as DSOs. So we distinguish two types of point of view. The first one is technical area, and the second one is users' behavior. So technical area, it means the ability to manage the technical structure of the network in the most effective way, allowing to create conditions for connecting new users while maintaining the stability of and continuity of supplies. But the point of view of users' behavior area. This is the ability of user to reduce or increase consumption of or generation, for example, by offering services, but not only because here we can also include some behaviors achieving based some kind of incentives through tariffs, for example. But this part is not the part of the report. It's not discussed in the report. So this is the basic understanding of the flexibility, because we have to also distinguish flexibility and flexibility services. This is not the same. Flexibility means the system ability to react on a current basis to any changes in both demand and supply, which theoretically could be an impact on maintaining the stable operation of the distribution system. So could you please next slide? Yes, so that's why we identified 3 types of flexibility. The first one is the technical or grid or maybe operational flexibility. We can call this in these 3 different ways. So this is the network operation, congestion management, and day-to-day operation. And it is the reaction of the system to disturbances of mainly local character, that is voltage and current overload. And this type of flexibility is a basic element in the system operation, day-to-day operation in the current operation of DSOs. So in other words, DSOs use available technology, available systems, and available assets to manage the grid. And it means that having that, we can increase flexibility. So the second one, the second type of flexibility is market flexibility. Here we think of flexibility, this part of flexibility, which DSO can buy procure from market participants as flexibility services. So this type of flexibility is, let's say, complementary in some cases to the grid flexibility, but of course everything depends on the justification and let's say possibility of good managing the grid. What exactly do we need? So and the second and the last one type of flexibility, this is investment and planning flexibility. In other words, network development plan. In this network development plan, each time we have to include not only technical parts of flexibility, but also market flexibility to design our grid, to plan development of our grid in a long term. This type of flexibility is not activated. There is no activation as in previous 2 flexi types. So next slide, please. Yes, and the second definition, which is important from the report, from the point of view of the report, is grid observability and controllability. So, of course, we have in the SOGL regulation the definition of observability area, which means TSO's own transmission system and the relevant parts of distribution system and neighboring DSO's transmission system, on which the DSO implements real-time monitoring and modeling to maintain operational security in its control area, including interconnections. So the definition does not define observability from DSO point of view, especially at low voltage level. So we understand observability. That's why we define observability in the report as temporal ghost total and topological awareness of all grid variables and assets. It is also the ability for any combination of system state and inputs to determine the system state in a finite time using only measurement of system output. So here on this screen, you can see also one of the charts from the first report prepared by Active Network Management Task Force. Here, 20 DSOs answered about grid observability at different levels of the grid. So as you can see, at high voltage level, we can speak about 100% observability, but low voltage level, as you can see, this is let's say the poorest observability of this level. Next slide, please. And yes, this slide it was mentioned by at the beginning of this webinar, so that DSOs needs flexibility for three different needs. The first one is voltage control, especially at low voltage level. And the second, this is local congestion management. And of course, due to a lot of new distributed energy resources, it is important to manage this congestion at the local level. And of course, grid development plan, as I said before, in this grid development plan, there is a need to combine two types of flexibility, that is technical one and market one. The next slide, please. So let me go very fast through the main concept of DSO grid observability. Observability in the grid means the ability to observe how conditions are in different places in the grid. This is done mainly by measuring of current and voltage, but also other types of sensors, something like states or temperature. So increased flexibility will give better knowledge about the grid and its behavior, and the ability to analyze in order to make the right decisions. So as you can see on this screen, the most important thing is, first of all, identify places in the grid where there are some problems, and how we can solve the problems. To do so, we have to know exactly. We have to identify it through different assets, in which places we have a problem, and what kind of problems we have. So all this data from the grid should come to data center, and then through using some let's say specified algorithms for this, can analyze what kind of flexibility we can use to manage the grid. So the first step should be to try to manage the grid using technical flexibility. That is why to use all assets, all available devices and systems to manage the grid, for example, through some kind of switching. But also, if the flexibility, the technical flexibility is not enough, we can just jump to the market and try to find flexibility, market flexibility, the good offers from the market, which based on which we will be able to solve our problems on the grid. However, this is only, let's say, general point of view, because every time there is a need to analyze which solution is the best one, maybe not economically one, but the best one for the grid to solve problems on the grid. So could you next slide, please? And now we have three different voltage levels. So the first one is the high voltage level, and how we what we should have to manage this high voltage level. So as you can see at the center of the slide, of course, SCADA systems with a module for importing special treats from the grid. Of course, to have these special treats from the grids, we need to have special equipment of the grid. And then, of course, we need to know standard signals from the grid, and then some kind of state estimation. Of course, based on all of this data, there should be a possibility to analyze all this data and try to find the best solution to eliminate this coming interruptions, let's say. But from the second part of this picture, you can see also some flexibility resources, but not only. Also some kind of equipment, technical equipment from the grid, and so signals from this part could be achieved as well, and the flow of the data have to be follow also to this flexibility sources in order, for example, to activate some resources. Next slide, please. And then low voltage, medium voltage level. This is the mainly the situation is common to the situation at medium at high voltage level. However, of course, everything depends on the topology of the network, and so the most important thing is here is to have, for example, fault location, isolation, and services restoration responses. However, of course, SCADA is important element. I think SCADA is the element. This is the element which is important for all network levels. So, and however, what is more, of course, smart meters at substations, at stations, and data from the meters allowing to prepare analysis how the grid is balanced, for example, and of course some equipment related to transformers, which under which regulate for which regulation could be done under load. So the next slide, please. And the last one, this is low voltage level. Here, the situation is the most complicated. The first thing is because because the topology is really complicated over the grid. There are not only ring but also radial network topology, and there are a lot of connection points which should be observable for the needs of the system. There are a lot of customers and prosumers. One remark here, because yesterday I had a conference and I heard some definition of new types of prosumer. This is flexumer. It means that prosumer can serve services, flexibility services to the grid. So this is something like yeah, remark. So, and of course, at this level, we can think not only about data from the smart meters, but we can think of possible data from home installations. So now we have a lot of projects which try to find a way how to use this data for the system needs. So a lot of data, a lot of informations, and very challenging to manage this level and this grid level, especially related to this coming data. So that's all from my side. Juan, the floor is yours.
Okay, thank you. Okay, let's move on to the more technical part of the report. So first, we will have a quick review of the technology. So don't expect to find a very thorough analysis of the technology, but we went just analyzing the technology today. We need to understand that it is very important to have interaction between different systems and different energy resources in different points. Communications are key, and reliable and affordable telecom are really important. So in the picture, what we have in the left side, we will find technologies we mainly use to communicate with our substations, primary, secondary substations, while in the right side, you have all the access, the massive access to prosumers communications. In fact, this is not fully 100% true. I mean, for example, in Iberdrola, we use BPLC for telecontrol as well, but mainly it works. So starting with fiber optic is here since 20 years, and it has become a standard. There are plenty of technologies. Many times it's deployed for other purpose, but normally I would say in most of the utilities is there, or in many utilities. And there are plenty of technologies. In Iberdrola, we use DWDM, and there are some others. If we move to cellular networks, whether public or private, we will find a range from the 2G, the classical GSM, up to the 5G. And in between, we will expect GPRS solutions or 4G, LTE, whatever. This is good because they are affordable and they are quite largely deployed, except some rural areas that they have a lack of coverage. Mass mobile, this is not so common, and it consists in a master station in a primary substation. Typically, you will expect technology like YSAN, but it's convenient because it doesn't need to prepare any network planning in addition. And narrowband P2MP, this is the classical radio, the VHF, UHF we use to connect with the crews, and it can be extended and can be a convenient candidate as well. The right side, we have a power line carrier in narrowband, typically used for meter reading and AMI, while the broadband is more used to connect the data concentrators, or public internet, which is a very good candidate because most of the DR has internet for other purposes. and it can be a nice technology to publish flexibility or to interact with us. Okay, please move on for the next slide. Okay, here we have the pyramid of technology. So main motivation today for A&M is to face the regulatory and social pressure to connect more renewable energy sources and to defer network investments by doing it, which is opposed to what we get paid with today with our regulation. But basically today, the main objective of A&M is to offer users a service for faster connection to the grid and not conditioned to reinforcement or network extensions. And at the same time, to prevent overloads and keeping the generation rights of the already existing connected there in real time. This is to the simple contingency, say N-1. In the long term, all the utilities we are seeking to be prepared to become a DSO in the future and to manage efficiently flexibility. This affects two main activities in all the utilities, which are planning and operation and the tools and procedures used for them. So, and this pyramid reflects a little bit the different states or the different levels of maturity we find in Europe. So in the base of the pyramid, we have the basic visibility, including meter reading. It's very important to know what producers or consumers are doing, and forecasting for planning and billing whatever flexibility is provided. So the 4 quadrants of active and reactive power are needed. If we move forward to operate flexibility, we need real-time values and SCADA capacities. Well, if we move to the next block, which is, I will say, perform control over flexibility, for that we need whether local automation solutions or more evolved centralized automation solutions. But if we move forward, the idea would be to really face all constraints in real time, and for that we need to run electrical network applications to fulfill all the constraints and to have full visibility with what's going on in our grids. Moving to low voltage network, as we will see, has additional implications. Normally we will face unbalanced networks and so on. Okay, next one, please. Next slide, please, Katerina. So yeah, so here we have a simplified diagram. So from the let's say the individual DER controller based on power electronics, where we could control voltage or the active and reactive flow. We could have solutions integrating an area, following a wider area, or even a centralized solution. In the report, you will find a list of informations to be exchanged between the utility and the DER, so to have a kind of standard set of information. However, we believe that the most robust solution would be a generic one, integrating in our centralized systems all the dealing with this flexibility. Please move on to the next one. And this is the ideal situation from our point of view. Will come in the future. We have all the actors there. We have the model of all the network, and we have model all the flexibility. We will find all our own flexibility controls, like a shunt capacitor or the tap changer of a transformer, that we can already change that. But in addition, we will have other controls coming from the DER that we will be able to put together in solutions based on optimal power flows, where we could put together based on market price, based on constraints, what is the most efficient solution. So please move on to the next one. Okay, this one is coming from my colleagues here in the planning department. So it summarizes what are the common flexible resources So owned by the utility, I mentioned already, the shunt capacitors, the tap changers, even storage systems, and sources or resources owned by externals. And here we have a myriad of things. So if we move to the right column, the key here is the acquisition. How are we going to reach them? At this moment might be with bilateral contracts, or maybe in the future more massive through platforms. This is something that needs from the regulatory point of view to be developed. But the services are crystal clear. I think it has been mentioned by our sponsor today and even by Eva. So basically we are talking here, if we speak about reactive power, we will talk about voltage control, or if we talk about active power to help with congestion management or even island control. Please, next one. Okay, and now we move on to the conclusions of the report. So one of the conclusions is not mentioned here, but it's obvious, is planning and operation will become much more complex. So probably, or for sure, regulation will have to change. Instead of being paid for what the network we install, we should be paid some partly, I don't know how it will be in the future, for a much more complex operation. For sure, we will need to maintain more devices. We talk about observability all the time, and dealing with them will be much more complex. But if we talk about the short term, what A&M is bringing, we believe, as it was stated before, some of the technologies are already there. If we talk about high voltage and medium voltage, so if we talk about automation and SCADA metering, and this is quite average already. These technologies are already starting or deployed in many of our utilities. However, if what we lack at this very moment and is really big, and we need to start now, first is if we are seeking the low voltage, and the low voltage will have plenty of flexibility, we need not to neglect the size. So scalability and sizing is really important. Think that a line segment in high voltage really stands for one segment, the same as the connection point in low voltage for a single customer. So the amount of the number of objects and the size of the network, it really becomes many times bigger, and dealing with that, we need to be prepared and to start now. Also, increasing observability is a must, but we need to be careful and optimize the investment. So we need reliable and accurate sensors that they will be deployed somehow massively at some point, but we need to remember maintenance. So then standardizing equipment is really very important. And I will say even consider remote access. So trying to reduce the number of trips going to this equipment. And the third point is investing in digitalization. We all know, so improving our network models, the inventory, the electrical parameters, connectivity, and if we talk about the low voltage, we need to know phase information and others, that it will take time. Please move to the last slide. And requirements for the utility. Okay, for operation, to operate flexibility, we need high observability and controllability. So we need to develop communications and interfaces with there. Hopefully, the more standard, the better to deal with all this. Secondly, for planning, we need to invest in IT tools for forecasting. So forecasting what the renewable sources are going to do, or what the demand is going to be, is really critical. And integrating flexibility in our procedures for planning is a must. So in parallel, we need, or one of the requirements is to update the planning tools to these new procedures, right? Then we talk about exchanging information between many partners, many sources. Here is very important, is a big requirement, is data protection and cybersecurity. So this is a must. So then we need a methodology to assess quantitatively the impact of flexibility, and there must be an agreement. So this is a requirement for regulators. We need to invest in digitalization inside the company. We have already mentioned in AMI, improve our ADMS, for sure, our inventories. I will say the GIS is a key technology here, inventories, connectivities. And finally, we need to build, or one of the requirements is to have a strong ADMS, matching performance things that these systems need to live also in storm conditions, and integrate all functions needed, as we mentioned, network applications to be able to use optimal power flows and optimal algorithms. And I think that's all from me. So.
Thank you, Juan. I will not let you go from the stage, and I don't even turn my camera on because you are the first panelist from the use case session. So we can start with you with the first use case on ADMS integration, a practical example from Spain and from Iberdrola in this case.
Mm-hmm.
So.
Okay, very good. So move to please to the next slide. So here, as I mentioned, from where are the requirements coming? And the requirements in our case, in Iberdrola, I mentioned I work for ADMS systems, is coming from the planning department. They want to connect new renewable sources, but without or not waiting to the network reinforcement. And then the thing is, they are open to not to guarantee the firm power, so to the nominal power, based on first they do their contingency analysis on the number of hours that there can be overloads or contingencies, and for sure, obviously, waiting for a future reinforcement. This is the case of Iberdrola, and the idea is to offer the distributed energy resources a faster connection to the grid. So this was mentioned before. So please move to the practical example we had in Iberdrola. Well, as I mentioned before, the strategy in Iberdrola, I brought back again this slide because our strategy is not to have this local automation that has some drawbacks, but to integrate all the logics in the ADMS. So please go to the next one. And here, well, this is the result. The result is what we have called the LANM, which stands for Logic ANM, and it's a watchdog program in our ADMS platform. This watchdog consider any logical and relational operation, as you see, and is able to send commands to the field. So the advantage is it is a very fast and easy solution. So we have one request we are going to see at this moment, for example, Valdeobispo, and we fastly can provide a set of a sequence that will help us keeping the network in good condition. The disadvantage is that this type of specific situations, and this is why we want to avoid this local automation, it requires parameterization. Think that the distribution network changes the topology, the market grows, and then you need to be rethinking the logics all the time. Periodically, you need to check that the logic is still valid. And then you need operation training for operators, because maybe in one point, the logic is different from another point. And then the more logics you include, the more difficult it is to maintain and to operate. Please go to the next slide, and we will go to the practical example, which, no, you went too fast. This is Valdeobispo. Well, in Valdeobispo, there are two transformers and a line. There is a hydro unit, and there was the request to connect a photovoltaic, a big photovoltaic farm. So we got the request from the planning department, did their calculations, and then we came back with this Logic ANM program. Can you move first, please, to the next one? So we we ended up with two logics. I mean, the logics are quite simple. You define some variables to check. Even you can define constants, and we ended up with two different logics. For sure, the program has a lot of user interface and usability developments to warn the dispatchers that the program is going to work with different alarm levels. And it can be enabled and disabled by the dispatchers anytime. So if they face problems, but if you see the logic, if we move to the first logic, where there is always a common point from where they can, it's called LANM, like the program, where they can active and disactive this sequence in particular. In the case of the logic on the left, the first logic, simply we supervise the current in the transmission line, and we define which breaker is going to be open. The constant is 600 because it's 600 amps the trip, and then we define the command, and we can include a delay for this command. So we will wait just the overload for some period, like a typical overload protection. In the other one, we have the same logic, but in this case we are fulfilling, in addition, the summatory of the two transformers, and we are talking here about active power. So in this case, the limit is going to be 133, but the effect is going to be the same. Please go to the next one. And this is how it is seen in the one-line diagrams. Here we have the evacuation line, which is the one which is suspected to be overload. I think among something like between 200 to 600 hours a year, it could be overload, depending on the different conditions of the hydro plant and the consumption on the two transformers. So please move to the next one. I brought this second implementation, is ongoing, but this one is interesting because it is connecting information from several RTUs, and here the logic simply make sure that the evacuation line between Urrutia and Collado, which are two stations, is really able or available. So here it was to give the permission for a wind farm, huge wind farm in La Señorita in Cofrentes, but the calculations from the planning department told us that this line had to be connected. So if you notice, the logic is just to make sure that the line is connected. Otherwise, they will disconnect the wind farm. So please move on to the next slide. Okay, this is how it is seen in the displays. So what I have already explained, and then please move to the next one. Too far. So simply the idea is to have more renewable energy produced with the same capacity. This is the idea of these logics. However, what we have discovered as well is that once that these logics have been developed, there are some other additional uses. We have found that this program has some subproducts. So at the moment, we are planning to use these logics for parallel transformers, which has not been designed to work in parallel, and the typical reactive power control in a distributed energy resource. So we have a capacitor. The capacitor will be connected or disconnected based on the cost fee. So it's very interesting, and the good news is that we don't need any additional maintenance or database to be created in a parallel in any parallel systems. We don't need any additional license or anything else. So this is the thing, and that's all for me.
Thank you so much, Juan. So as I said before, if there is any questions, please add them on the Q&A tool, and then on the round table with all the speakers, we'll proceed with the questions for the theoretical overview and for the presentation of the use cases. And now next to the stage, I invite Tania Vasquez from RH Spain, that is already on the screen. So Tania, welcome, and the floor is yours.
Hello, everybody. My name is Tania Vázquez. I work for EDP Networks Spain, and I'm going to talk a little bit about exploring flexibility in low voltage network. Please move on, Katarina. I'll move on again. Okay. Smart meters have opened up communication to the low voltage grid, allowing the flow of new data from customers to our systems. Monitoring low voltage grid at customer point, data management and expert knowledge are the key to reliability, resilience, and operation excellence. Thanks to that keys, in these days, failures, as for example, could phase or neutral loss, are controlled 24/7 in our control room, even not noticed by the customers. If you look this kind of tree diagram, this is our low voltage grid. Power flows from secondary substation goes to low voltage feeders, to the branches, and finally, as you can see here, to the smart meter or houses. With the smart meter, for first time, we are able to monitor the energy that flows to the last point of the grid or customers. If we use that data in a smart way, we are not only able to do meter readings, we are able to detect failures, for example, could phase or neutral loss through some alarms of the smart meters. So smart meters, it was the first step to observability in low voltage grids. Please move on, Katarina. Smart meters has allowed a technology evolution. Monitoring at feeders are now a reality as well. As you can see in the picture at the left side, we have a low voltage switchgear conventional with fuses, but now with new sensors at feeders as well. New feeders data collection is achieved through the installations of sensors from the feeders, new software and data system. EDP Networks Spain have been involved in an important rollout of these sensors since 2018. As you can see again in this kind of diagram, this tree, we have a monitoring now in low voltage feeders. So with the smart meters at customer point and these new sensors, we have a high level of observability or monitoring in low voltage grid. With these new sensors, we are able to detect, for example, short circuits in branches or low voltage feeders or blown fuse in this low voltage switch gear. Please move on. Now, we are seeing an example of observability. We have, for first time, glasses to see what is happening in low voltage grid. But we want to pass to action. EDP Networks Spain is working now in a research project for switching feeders by remote. As you can see in the image at the left side, you can see one prototype of low voltage switchgear in 2 secondary substations, which are now operating in our grid since May of this year. We have 2 secondary substations with this new low voltage switchgear with fuses and circuit breakers as well. So now, when something is happening in our branch, low voltage branch or low voltage feeder, and we detect with our new glasses as smart meters that there is a failure, we will be able to do remote feeders switching. Please, next one. So this is the low voltage grid of our thoughts. We want a low voltage grid observable, temporal, geospatial, and topological detailed information, despite we need all this data because otherwise smart meter data are not useful. We want it dynamically reconfigurable, and we want it reliable. But we know that can be not enough. As you can see here, with economic electrification, our tree or our low voltage grid, event time is more loaded. Please move. Okay, this is a real problem now in low voltage grid. I want to explain because we think this is going to be increasing in the future. New low voltage generation results in overvoltage in our grid. Sometimes even the customer with generator complains. Neighbors can complain as well. These generators are just informed to us. Installation technicians many times oversight the photovoltaic panels, aggravating the situation. So this is a case we have to do creative technical solutions. What are the definitive technical solutions for this, for us in this kind of situation? We can reconfigure. This was an example of technical flexibility in low voltage grid. This is real for us, but this can or not solve the situation. We can have tap changers as well in transformer at secondary substation, but you realize that can or not solve this local situation. Load balancing can or not solve on other technical solutions. And this is a problem, a real problem at the moment we have to solve. You can see here that we have a lot of challenges in low voltage grid: economic electrification, grid planning, and market flexibility or flexibility services. That's all. Thank you, everybody. If there is any question, please.
Thank you, Tanya, for the presentation of this use case and another example from Spain. Now we'll go through our third presentation on the use cases. And now I invite Emanuele, who's already on the screen, for the presentation of this experience from Greece, from Edno, and a close look on the Coordinate project. So I give the stage to you. Welcome.
Hello, everyone. Thank you, Katarina. I will present you a use case related to the DSO consumer coordination for the integration of distributed flexibility in a market environment. In the next slide, next slide, please. This is a demonstration that was developed through Coordinate project. Coordinate was a project that was funded by Horizon 2020 and focused on the DSO and consumer coordination. A few words about grid services and standard products. First of all, in order to ensure the development and the stable operation of transmission and distribution grids, system operators make use of grid services. Grid services are defined as services provided by DSOs and TSOs to keep the operation of the grid within acceptable limits for security of supply, and are delivered mainly by third parties. In order to enable a market-based allocation of these grid services and to enable the market parties to effectively bid into these markets, we need to define products for these services. Standard products are defined as harmonized products for the exchange of grid services, which have some common characteristics. The assumptions made here that the standard product can be specific to one grid service or more, and also multiple standard products might be defined to deliver a certain service. So in the next slide, we can see why do we need all these grid services? The reason is that the energy transition has led to the installation of a lot of renewable energy sources, and this creates also a lot of challenges. The energy transition creates a lot of challenges in the field of energy balancing, the safe grid operation, and congestion management. On the other hand, we have the installation of generation in distribution grids, as well as new developments such as active network management that provides opportunity to DSOs to perform active and reactive power management in our grids, and to participate also in the management of the transmission grid. In this view, the coordination mechanism that agreed between DSOs and TSOs are necessary. In the next slide, please. This is an indicative list of grid services that can be procured through the market environment. The potential flexibility service providers include storage, renewable energy services, EVs, buildings, small generators, cooling and heating systems. The buyers of the services are DSOs and TSOs. And the next slides, we can see how a product is standardized. We define specific attributes, and these attributes are specified within the contractual agreements between the TSO, the DSO, and the flexibility service provided. As I said before, the standard product may be specific to one grid service and address the requirements of multiple standard multiple services. So in the next slide, these services and products must be provided and procured through a market, and there are different coordination schemes. There is no one fit for all coordination scheme. This is because there are local circumstances and specificities, market maturities, regulator conditions are different between countries and systems. As a result, there exists a multitude of coordination schemes, which we can see in the screen. And we have, before choosing the appropriate coordination scheme, we have to answer some key questions. Where is the need located in the system is the first question. Is it a central and local, or a local need? Who is the primary buyer of the flexibility? Who is the seller? How many are the primary buyers? And if the TSO has access on the distribution level. Next slide. In our demonstration, we have two demonstration sites, Mesogia, near Athens, and Kefalonia. The services procured are congestion management and voltage control, and the products are reserve congestion management and non-reserve congestion management and for voltage control, steady state reactive power and active power product. We use two coordination schemes. The first is the multi-level market model. In this scheme, the flexibility service providers that are connected to the distribution system can provide flexibility also to the transmission system. After the DSO, the distribution system operator, has assured that the activation of this flexibility will respect the DSO grid constraints. Therefore, the transmission system operator can eliminate voltage violations or congestions in his network using flexibility provided by flexible resources connected to the distribution system and to the transmission system. On the other hand, the fragmented market model, each operator, DSO and TSO, can procure flexibility only from the flexible resources that are connected to their network. So the flexibility resources which are connected to the distribution system can be used indirectly for the elimination of voltage violation in a transmission system through the proper power exchange between them. So there is a agreed level of power exchange between DSOs and TSOs in order to achieve the elimination of voltage violation or congestions. So in this case, the cooperation information exchange between DSO and TSO is crucial for deciding the appropriate level of power exchange. In the next slide, we can see the time frames we use for congestion management voltage control. We use both day ahead, intraday, and near real time. We use both capacity and energy products, the two market models, and the flexibility service providers include small renewable assets, large generators, aggregator, consumers, storage, and other flexibility service providers such as water pumps. As we can see in the next slide, there are some pictures of the flexibility service providers, and the next slide there is a picture of the water pumps that are used as a flexible load in order to provide flexibility in the distribution and transmission system. For this platform to work, as you can see in the next slide, we need a number of software tools, which include the forecasting. We have to forecast the day ahead in order to ensure that to spot the voltage, potential voltage violations or congestions in the networks. We need a wide area monitoring state estimation system, a platform, a market platform that takes the bits and clears the market, an aggregator tool, which is oriented to users who have the role of aggregator, also a tool for transmission system operators and distribution system operators, monitoring service, reporting service, and a common high voltage and medium voltage network model. In the next slide, we can see a view of a front end of the market operator. The market operator can see the bids, the prices, and the quantities offered for the service procured. And in the next slide, we can see the front end of an aggregator. An aggregator can provide a bid by using this toolbox. So an aggregator can use this toolbox in order to submit the bid for each service procured. In the next slide, you can see the architecture of the local market used. There are two main mechanisms for procuring services. The first is the rule-based, which is dictated by the technical requirements and the grid codes. For example, RFG network code imposes some obligations for the units in order to provide reactive power, but also there is the mechanism, the market mechanism, and we examine mainly this market mechanism for procuring the products. The market has three stages here: the local market, the day ahead, the intraday, and the real time. And the products are both capacity, which is procured in day ahead and intraday, and activated in the real time, and energy, which is procured in all time frames. Next slide. Here is the algorithm of local market formulation. In the day ahead and the intraday, we need to minimize the capacity and energy cost, while in the real-time market, we minimize the energy cost and the reactive power cost. Next slide. The one crucial thing is to harmonize the local market with the existing wholesale market. And we can see that here is the existing wholesale market in Greece. We have a day-ahead market, and then we have the solution of the first intraday auction, then the ISP1 by the DSO, and then we have the second intraday auction, which is followed by an ISP2 by the TSO. Then we go to the third intraday, and then we have the balancing market after the ISP3. In the next slide, we can see how we shall fit our local market depending on the market, on the coordination model we will use. This is the picture of the fragmented market model. In this market model, we have a fixed net load between DSO and TSO. And after receiving the first solution of ISP1, we use the results in order to solve the local market, and then we go to exactly in the same steps, coordinated with the wholesale market. In the next slide, it is the same concept, but the difference is that we now have a multi-level market and not a fragmented, so we don't have a fixed load between the TSO and the DSO. So some examples in the next slide, how to resolve a voltage control issue. If we can go to the next slide. We have the anticipated overvoltage in a distribution feeder. You can see that the voltage is up to 1.1 per unit in this feeder for several buses. The solution here is the reason for this overvoltage is the reverse power flow from renewable energy sources, and the solution is to provide downward flexibility. So in the middle picture, we can see the downward flexibility activated when we use the multi-level market model. And in the right-hand picture, we can see the fragmented market model. The difference between multi-level and fragmented market model is that we need to activate in the fragmented market model, we need to activate both downward and upward flexibility in order to compensate between them and to achieve a fixed power exchange between the DSO and the TSO, while in the multi-level market model, we don't have to do this. Similar are the cases in the next slide, where we have the undervoltage issue, and we can see in the next slide a similar case with congestion issue. We have the activation of downward and upward flexibility, and we can skip the next slide and go directly to the slide. Next slide, please. So we have an evaluation of this demonstration. We examined the cost of upward and downward flexibility and the volume of transactions during the examined period. We can see that the average cost per service for the examined period is around 90 to 100 euros per megawatt hour, depending on the use case examined. And in the next slide, we can see that the upward flexibility was a little bit cheaper. If we can go to the next slide. It was a little bit cheaper, and this was the downward flexibility represents the losses of renewable energy sources for their curtailments, while the upward flexibility, the activation of production. So in the next slides, we can discuss some lessons learned from this demonstration. First of all, the bit location is required due to the distribution network radiality, and this decreases the local market liquidity, because we can have a different local market for each distribution feeder. The TSO experience shows that the location of the bit is important also to the impact of the surge flexibility. The transmission system is not radial, but there is different impact of each bit. Each feeder is considered as a separate local market. So we have to facilitate the market solution and data handling as smaller networks are considered. The bits might be transferred to another local market when we have a configuration of the network. And so there are some difficulties introduced when we have transformer congestion, high voltage to medium voltage transformer, when we have to involve many markets, many feeders. Reactive power products are required for voltage control. Currently, few resources can offer this type of products in the distribution network. In the next slide, the flexible provided diversity is an enabler in more efficient grid issue solving. Different FSPs are best suited for different needs of flexibility. And also the introduction and operation of cooperative market models would be beneficial for flexibility service providers. But this would increase the system operator cost. In the next slide. When we have no interaction and bit exchange between local market and TSO market in the day-ahead and intraday time frame, the advantage is that we increase the liquidity of the local market and we avoid the potential network issues due to the activation of flexibility by the TSO, because the DSO does not have a good view of network state in the future due to demand and renewable energy sources uncertainty. The disadvantage is that we decrease the liquidity of the TSO market and we give less incentives to the flexibility service providers to participate in the local market, since they are excluded from the wholesale market. When we integrate congestion and voltage market with balancing market, on the other hand, the advantage is that we reduce the balancing cost and we increase the participation of FSPs in the market. So the challenges, however, are to the market solution and the data exchange handling, because it becomes more complicated. And in the last slide, we have to address the issue of communication. There is a lack of harmonized interfaces that enable market across for FSP value stacking across timescales and different markets. This is due to solidified processes used by system operators and the private sector. Communication protocols paradigm shift is difficult to achieve. Regulation around data responsible party is still in the making. Smart meters provide use proprietary software and standardized protocols to transmit data. And there are stalls in smart meters rollouts. The data exchange standards are yet inconclusive. We have to move from localization of standards to standardization based on data exchange platforms, and also have to address the lack of standardization for flexibility market. The baseline calculation procedure for pre-qualification of flexibility providers, market clearance, state estimation, and forecasting. So this was from my side. I would like to thank you. If you have any question, we can discuss it.
Thank you, Manolis, for the presentation and for a close-up also on this project coordinate that finished this year. I think there is very important lessons learned here, and for sure we will tackle some of them on the discussion table, or I will come up with them for us to go there. Now I give the stage to Siors. Sorry for the pronunciation. My Dutch after 1 year still not that good.
No problem.
And I give also the permission for you to share. I hope you have it now. Maybe we can test it. Can you try to share the slides?
And the host disabled participant screen sharing, so I don't know if we can manage that.
I will ask my colleague, Tiffany, to help us on this. Let's just wait a second.
If it's really difficult, we...
Can you try now, please?
Yeah, I'm pushing the button, but it's not...
I will stop share also to help.
Now yeah, this works. Sure. So, do you see my screen now?
Yes, go ahead.
Okay, thank you. Good morning, everybody. My name is Sjors van der Heijden. I work for Stedin. It's one of the Dutch DSOs. We are responsible for interesting part of the Netherlands to distribute the energy. For example, cities like Rotterdam, The Hague, but also the harbor areas in the southeast. But we also have rural areas, so quite different areas to manage. The slide that you see has a template of Netbeheer Netherlands. It's a cooperation between all the Dutch DSOs and our TSO tenant, where we cooperate on different topics. So you could see it maybe like a national version of EDSO. And today I want to talk you through what we are working on since 2020, which is a national standard for the DER interface, which we use for active network management. Yeah, so first I want to show you an example to see, okay, where could you position the real-time interface and how we typically use it. It's an example of situation that we have on an industrial area in Rotterdam. And normally we have the redundancy in our grid. So if something happens, a failure or maintenance, then one component can take over the part of the grid. But that's not mandatory by regulation and is now limiting the amount of customers that we can welcome in our grids. So in the future, we will lose that N-1 situation. And that's okay. If you have this situation, you still can manage the grid, but it gets exciting if something goes wrong, because if a failure will happen, one transformer has to take over and will be overloaded, and you can manage that for a short period, but then you need to undertake action to come back to a stable situation, or otherwise you will lose that part of the grid. So that's where we need the possibility to interact with our customers in real time. So these are situations where market options are not in time. So you have to have a direct button that you can hit to send set points and also get data back from your customers. And till now, every grid operator has its own interaction to customers. So that means that if you are a company that does a lot of projects with sun parks on roofs or wind parks or whatever that you have to deal with different standards for different grid operators, and our goal is to standardize and harmonize that. So some background. What we want to achieve is that we can guarantee the grid safety, so that we can manage this type of situations, as I showed you, make a better use of the grid capacity, and comply with the regulation, because till now often the RFG is mentioned in the contracts, but there is not always implementation to make use of the interaction with the customer. So we are looking for a harmonization, standardization, as I mentioned before. What we do is we made a functional specification that is supplier independent, and our roadmap is to start with physical components with the RTU and a telecommunication unit at the customer endpoint at the customer location. But in the future, we want to have a more central solution. Our approach was that we don't want to figure everything out as the grid operators and then forced to use that for the customers. So what we did is that we had a collaboration with our external stakeholders, but also with different knowledge institutions. We make use of international standards, and it's a iterative development. So we are now in the implementation phase, and while we are building implementations, we get feedback on our specifications, and in different iterations, we improve our standard specification. So we are now working, as I told you, about on the implementation. So we stimulated market parties to do product development for as well the system operator side as for the customer side. So we see now appearing different solutions based on the technical specification that we made. We work together as system operators as well to get the implementation as good as fast as possible. So we learn from each other, and we work together with DNV GL in the Netherlands. They made a test plan so that the solutions that are built on the specifications are also compliant with the specifications. Now we're now working on as the three main DSOs, the bigger DSOs. We said, okay, the category B, so that's from 1 megawatt to 50 megawatts. We want to start rollout next year, and the focus will be mainly on the areas where we now have issues with the capacity, and the use cases will also based on the capacity. The use case like I showed with the animated slide, but for future use cases, the solution or the technology should not be the limiting factor. And the main challenge is that this is a new type of service that we have to provide. So we have to get everything in place in the organization. So the right components, logistics, people that can install this type of equipment, because the DER market is really booming. So we see a lot of new DERs coming into our grid, and if we want all those new customers to have DER control to have implemented, that's quite a challenge. So the basic principle, this is just an overview of all the company or organizations that are working together on the standard, but here more in general. So we're talking about two endpoints, both based on the specification that we made. So one of the system operator, one of the customer, and we interact to each other with Ethernet connection, and our requirements give information about the exchange protocols, the messages, also security measures. And on the other side, there is also requirements regarding the behavior. I saw in the Q&A a question about what's happening if you don't have communication or a blackout. We figured out a lot of scenarios that can occur, and you also have to have an idea. Okay, if there is no communication available, how do you deal with that? If you one of the suggestions that we had was, okay, if you don't have communication, then you're not allowed to produce energy. But if you have a really big telecom outage in your country, then that will result in a lot of power that was promised to deliver in that period, and if you don't deliver it, you get a lot of imbalance. So that's also a situation you don't want to have. So we also described different fail-safe modes to assure that loss of communication will not result in large issues, and that you still can keep your grid online. Our approach, so how did you come to the specification? It's main success factor was the collaboration between all the different stakeholders in all the different phases. We had a coordinating working group and a technical working group. The coordinating working group started with functional requirements, and then the technical working group translated that to the specification, and we also continuously had interaction with a subject matters experts group that we had with people more in the supplier business of PV parks or things like that, in inverters, things like that, to see, okay, does the specification make sense? Will it work? Things like that. So the basic approach was to start with the use cases, translate that to the requirements. One of the foundations that we used was the model, the smart grid architecture model, as you see on the picture. We also used that models. On every model, we had to make design decisions, which also has impact on each other. And where we had to make design choices, we made the multi-criteria analysis, and we discussed that with the different people or stakeholders involved to see, okay, what is the best option for now and the future. So for the RTI, the real-time interface version 1, we that's the physical implementation at the customer. We said for the communication layer, we had 3 good options, as noted here. For the information layer, mainly because of the common information model 61850 was the best option. So we also used that for the communication layer. And all of those were good or possible to implement. And we also look forward to the second version of the real-time interface, where we want to have more central approach without physical components communicating in the grid. 6150 is also a standard that we can build up further. We also looked at international. So when we started with the development of the real-time interface, we talked with other grid operators in Europe. So what you see here is not the standard for the whole country. It's probably the standard of one or a few grid operators in that country. But what we see in common is that more and more grid operators use IP-based interfaces. They're using IC standards, semantics, and they do the control on the common coupling points. To elaborate a bit further, what we mean by that is that if we, for example, send a set point with a percentage to a customer, it's not necessarily exactly the percentage of the production capacity, but what he can deliver back on the common coupling point. So that keeps the option open for customers to, for example, with batteries, that if they receive a set point that they have to lower their production, that they keep the production on the same level, but they put that energy in a battery instead of bring it up to the grid. Now, our experience so far, one of the results is that we have an SCD file, which is a 6150 description file, which we shared with the different parties that work on it, so they can load it in and to see if their products can deal with that. Currently, the tests are at full blast, so we have different suppliers that build customer endpoints or system operator endpoints, and they are testing it now. We are still positive about the design choices that we made. We experienced that 6150 is for mainly the customer part quite new, so sometimes you see some challenges in how they can implement that or need extra gate arrays or data mapping to connect that to their energy management system of the production location. But still, it's a good standard. For the future, currently the most grid operators have their own interface, which is limited in functionality and also specific for each grid operator. We're now working on the implementation of real-time interface version 1. So then we have a standard for the whole of the Netherlands, which is a functional interface. So we have more possibility regarding functionality, but we still need physical components to install at the customer. And now we are also starting up the development of version 2, which is still a national standard, but where we have the option to work centrally, because a lot of what we get as feedback from our customers is that they say, okay, we are already controlling our production locations from a central point. We have connections and managing tools to control our production locations. So can we use that connection in the future to do also the real-time interface for the what the grid operators need. So that's something that started now and will be worked on the coming period. Yeah, so a quick presentation, quick introduction about the real-time interface. I think the slides will be shared as well to you all. If you use this link, this website, you can find explanation about the real-time interface, which will be in Dutch, with the components of the documents like the technical specification or the compliance verification are all written in English. So if you have interest to see how we implementing the real-time interface in the Netherlands, or if you are interested in to deliver standard solutions for this interface, then you can find the needed information on this website. So thank you, and then I give the screen back, or you can take it back if you want to.
Yes, I already took back. Thank you. Thank you so much for your presentation and for the presentation of this use case and the example of Netherlands. The presentations will be shared after, also the recording of this, And now, before I give the stage to Gerard, I just want to go to the fact that this is the last use case. So if you have some questions for our panelists, I would ask you to add them now on the chat of the Q&A session. And also our panelists will go through them and select the ones to be answered on the round table, and the other ones they will answer offline directly to you. So welcome, Gerard, and you are the last use case, but not less important. So now I give the stage to you. And
okay. Thank you. Morning, everyone. I'm Gerard Boyd from SP Energy Networks. We are one of the UK DNOs, and we're one of the only DNOs. We're the only DNO that covers both Scotland, Wales, and England, so all three mainland UK countries. Although I've the responsibility for the Active Network Management project, I've got a number of other responsibilities, which I thought I'd call out just another one quickly, which is as I've also led on our market flexibility offerings. So last year we tendered for about 1.4 gigawatts of flexibility services for the distribution network, taking us all the way out to 2028. So that's one I'd happy to field questions about, or to come back to speak in more detail about in future. Okay, so I'm going to speak briefly about our journey on active network management. So it started back in 2016 with our first A&M scheme, which was under the Accelerating Renewables Connection, or ARC project. And there was a real clear driver need to do something with active network management, or to do something to address some of our challenges. So at that point, we had about 25% of our GSPs were actually exporting, and that's increasing over time at the moment. And that's primarily driven by the adoption of onshore wind. And also there's challenges well with long lead times for reinforcement and increasing pressure from customers to connect to the network. So with traditional design approaches, our traditional design approach, when we're looking at what capacity is available, we're looking at the contracted capacity of connected generation. So albeit some substations or GSPs may be constrained from a contracted perspective, if you actually look at real-time monitoring and real-time control, there actually is substantial capacity that can be released if customers are connected under A&M. So the kind of shown here is our active network management philosophy. So this is effectively real or near real-time control. So we've got a number of generators connected under this. And generators in that area could be connected under A&M, or could be under a full firm connection from a historic connection. And we have upstream monitoring points feeding into a system that is effectively looking at load flow analysis, power systems analysis, and network topology to identify at the points and constraint points, what are the set points in real time that need to be given to customers. So if customers are controlled under the active network management scheme, they'll effectively be given set points and trim points, and those are dynamic over time. And obviously, given that it's primarily wind, it's quite unpredictable in short periods of time. So this is where we came to this solution that could look at that system analysis to provide those set points in real time. So those generators, if they're provided with a trim, they've effectively got an outstation at their premises, and those customers will be trimmed down to a safe level for the network in terms of thermal limits. Once those constraints are removed from the upstream, then those generators are allowed to generate back up again. And I think that one of the keys here was that a number of these customers previously were connected under what we term a load management scheme, which was effectively a hard overload trip. And those customers were quite dissatisfied with the service, because if it's a wind farm and they're being tripped off frequently, it's not just the loss of generating output, it's also the damage or potential maintenance issues with their plant. So the concept that we've got a dynamic, even if they're trimmed to zero, they're not actually switched off. This is a much better offering for our customers. The The last point I want to just talk about here is also that how they're governed at the moment. So this is each customer connected under our active network management systems is governed under the principles of access. So who gets first access or otherwise. And to date, that's typically been through what we call LIFO stack. So it's last in, first off, which kind of mirrors the UK commercial mechanisms for how customers get access to the network. I'm quite keen moving forward to be more dynamic with that and look at alternative options. We've looked at shared capacity. We've looked at technical best. We're even looking at and discussing with our system operator a much more commercial mechanisms in terms of how those principles of access are defined. But at the moment, it's largely governed by this LIFO stack. If you want to go to the next slide, please. Thank you. So in terms of our system architecture, mine isn't quite as pretty as Juan's in terms of the description here, but you'll probably notice quite a similar topology. And I think there's a couple of reasons for that. So I think where we're coming from is we wanted a scalable solution. So that's where we've got this central system, which is effectively installed within our control rooms and is scalable to any number of constraint management zones. So that's connected to local controllers or constraint management zones. And those may be at one grid supply point, but they may have a span of control of a number of grid supply points. But again, the central system can be expanded to include more constraint management zones, and I'll show you our ambitions as we get to the end of the presentation. And for each of those CMZs, we've also got A&M outstations. So these are at the customer's premises, and similarly, they're scalable so the CMZs can have multiple customer A&M outstations that effectively control the customer equipment and set those set points in real time. So that's our kind of vision for how this works. We've kind of got a main brain that does all the complex system analysis piece, and then you've got local controllers, which also have, as you know, in the previous presentation, we talked about kind of fail-safe modes. So that both the CMZs and the local A&M outstation controllers both have fail-safes designed within that are appropriate to what impact it could have on the network. So it might be curtailed to zero, it might be curtailed to a lower percentage, but they've all got that programmed in to provide a fail-safe option. If you go to the next slide, please. Thank you. So this is just an example of one of the CMZs. So the kind of blue and green circles there are effectively our substations at 132 kV and 33 kV. And I'm not going to spend a long time talking about it, but effectively we've got a number of measurement points. So the transducers are actually, most of them in this CMZ are actually on the 132 kV network, which in Scotland is actually a transmission voltage. It's not in England and Wales, but it is in Scotland. So you've actually got transmission measurement points because a number of the constraints are based on the transmission network. So those transducers will feed into both the local CMZ controller, and the local CMZ controller feeds into the central system. Any curtailment decisions or any curtailment calculations are then made and then provided to the customer outstation, which you'll see the example of in the bottom left, which is down at Glen Chamber Wind Farm, which I'm actually quite pleased to say went live in terms of A&M control just yesterday. So they're now being controlled day to day by the active network management system. So that's a kind of topology of, we've got multiple CMZs that look like this. So you can also notice the controller is in Newton Stewart, but it can actually cover a number of local, down the bottom left, second from first up, but it actually controls and has got a span of control of multiple grid supply points and 33 kV substations, mostly based on what's local telecommunication requirements and capabilities. If we go to the next slide, please. Okay, I'm not going to spend a long time talking about grey boxes, but I think there are a couple of key points to bring across here. And one of them is again what Juan mentioned earlier on, which is standardization. And I think if we're going to be scalable And with the deployment of active network management, we need a high level of standardization. It needs to look, feel, sound, and smell like part of the furniture in our substations. It needs to have standardized, equipment. It needs to have ongoing, ongoing O&M contracts and policies and procedures established. And I think if you just look at, I've kind of drawn out if you look at the top left of the screen there, you'll see the original pilot in Dunbar, and whilst functional, I'm sure there's some protection and/or telecommunications experts on the call that would be aghast at the state of the Faroes there. But if you look at the new installations, it's fully designed. It's very clearly, part of the substation infrastructure and clearly designed. So that whilst it is again picture of your boxes, it's a very important part of deploying CMZs at scale, is that standardization. Okay, if we go into my last slide, please. So I just want to talk briefly about our deployment to date. So we now have a central system live in our SP distribution, which is the North of Scotland license. We're developing the central system for our SP ManWeb license, which covers England and Wales. So once those are both live, that gives us that scalable solution to deploy more CMZs over the coming years. We have had some interesting challenges with SP ManWeb. Quite a number of the circuit topology there is meshed, which becomes quite complex when you start looking at systems analysis and how A&M could work to provide set points dynamically. You need significantly more measurement points or more sophisticated analytics to actually arrive at the optimal solutions. We now have two CMZs live, with a further 2 scheduled before April. And in terms of benefits to date, so we've got some information that we could share on our website about the benefits that Dunbar has created. So the initial innovation project was 8 million. Now deployment is cheaper than that going forward, but that initial deployment has resulted in what we calculate to about £61 million in societal benefits. And just a part of that equation below that is looking at the tons of carbon saved due to the amount of gigawatt hours that the A&M system is effectively allowed to take place ahead of conventional reinforcement. So some of the generators in Dunbar connected five years ahead of when they would connect if they waited on conventional reinforcement. We've also got quite ambitious plans over the coming years out to 2028, again, the end of our next price control, which is the ED2 moniker in the bottom right. So we find out our final determination outcome next week on that. We were quite positive, but we were setting out ambitious plans to deploy another 22 constraint management zones out to 2028 with between 0.6 and 1.5 gigawatts of connected customers potentially, based on who chooses to connect with us and who chooses to contract with us over that period of time. So that's the end of my presentation. Happy to take any questions when we get to the Q&A.
Thank you, Gerard. Thank you for the presentation of the last use cases. I think it was a very good finishing of this round of use cases that we present also on the GoFlex report. So now I invite all the speakers to come on the stage, this online stage, with their camera on if possible, in order to answer some questions. I'm very happy to see that we have a lot of participants on this workshop, and we had a lot of questions. Our panelists were working on answering the questions offline, and there were selected some questions to put here online for all of you to answer. And I don't want to delay more also because we are going short on time. So I will start with a question for Ivan, that is regarding how much does the IT infrastructure cost to observe the low voltage grid, and now to activate the low voltage level flexibility options. Will each heat pump need a kind of SCADA node, or only the large ones?
Okay, the question is, I guess, to to me. And so thank you. First of all, thank you very much, Guman. If I don't know if I pronounce well the name, but yes, I know your articles, and I know that you are a really knowledgeable person, and you know very well the topic. So forgive me because probably I am not able to answer all your questions. However, this one I will try to answer, and thank you for the email. I didn't answer this, but I will try to do this now. So yes, of course, I am not able to give you a real amount of financial, how it will be, how much it will cost to implement all of these solutions we are speaking about. We are pointed in our report, but this is not the case. So we would like to just present the let's say the situation. Maybe in the future, maybe not, maybe some kind of final situation at the market, situation which we would like to achieve in the future, but perhaps this is not necessary. And we underline this in the report that achieving the full observability of the grid, especially at low voltage level, it is really difficult and really let's say long process, but perhaps, and I am not sure if we achieve this full observability at low voltage level. And you are right that maybe sometimes it is better to try to predict and try to incentivize customers through some kind of let's say tariff, maybe to just use to just have on the market more this explicit flexibility. In other words, flexibility coming from the behavior of users connected to the system. And about these heat pumps, there is no need to have SCADA and to have data from all heat pumps. Again, this is DSOs have to know how to predict this different level of amount in different periods, amount of energy. So this is there is no need to have this kind of observability at let's say each point in house to have data from this. However, we need to and what is more, there is no one model of one for which we can define as 100% of observability. So for one DSOs, there will be only 2 points with smart meters, and this kind of observability will be enough to manage flexibility. For the other, maybe it could be 10 smart meters, and that's all. So I would like to just say that the level of observability depends on the needs of the grid in particular area. So related coming to these heat pumps, yes, we know that there are a huge development of this kind of heat pumps, and but still this is only the additional load in the grid. So we have to predict this. And if you know, but of course, for some reasons, maybe we should know more about this this heat pump operation, especially when we think about behind the meter flexibility aggregation. So in other words, if you have behind the meter different kind of sources which would like to participate in the market of flexibility, and each of them would like to have different aggregator, then you can just try to manage this in a different way. However, for distribution system operator, the most important thing is what we have at connection point, how much of energy we have there. So thank you.
Thank you, Eva. I think it's more clear now. I will jump automatically to the next question for us to be able to answer as much as possible. So for Sorge, we have one question regarding communication lines. So if you need communication lines to power the power lines and you need the power lines to operate the communication lines, how do you restart the whole system after it went down?
Yeah, I don't want to spend much extra on it because I think we already mentioned in my presentation and the presentation from Scotland, we have things, we thought out scenarios and we have fail-safe mechanisms that ensure that without communication you can still use the most of your grid. So it's not optimal, and if you have telecommunication that's always reliable and is never down, then you maybe can even use more in your grid. So maybe it's in some part a limitation because a fail-safe modes will not catch everything. So then you have to be a bit safe about what you can do, but hopefully that gives an indication how we deal with that situation.
Thank you.
Sorry, Katarina, you are muted.
Yes.
Thank you. So this is for Juan Martinez. You have a question regarding primary control. So primary control just reacts on the frequency signal. Is this flexibility a service as well?
Yeah, I think there were a couple of questions regarding frequency.
Yeah.
So I think it was explained quite well by Eva that frequency is not part of the flexibility expected from the DSOs at the moment, because really, so keeping frequency in the right value, which maybe is 50 Hertz, forces the system operator to keep a balance of generation and load, okay, considering the losses as well. As far as all the big generation is connected to transmission, that makes sense. What we are talking here is that a large amount of distributed generation will be plugged into the distribution network, and I am sure we will have to get in the next future. We will need to answer this, and this is done. There are already means to do that. So typically, the generation control is done by a program called AGC, Automatic Grid Control, and it could work per areas. So you could assign a volume per area, and let's say we assume Iberdrola, for example, is 40% of the distribution network. We might receive the mandate to keep 30 or 20% of the frequency. So, but then we will need to have the rights to balance our stake. It's called the area controller role, just for you to know. It's a very interesting question because this will come in the future. Today is not considered at all. It's for TSOs mostly.
Thank you, Juan. And that gives me the next point on the TSO-DSO coordination. So this is for Manolis with a specific focus on coordinate. What are the barriers for a rollout regarding what you present and what was discussed?
The question for me as well. I think that there are no barriers. I think this well, one of the things that they are discussing is that the TSO wants to have visibility of generators, or at least the big generators, because they have this responsibility of keeping the frequency. They need to check, so they cannot neglect what is happening in distribution in terms of generation and load. Otherwise, they will be working with wrong assumptions, with wrong values. And then the thing is, if the generators really publish or have visibility of what they are doing at the TSO level, the DSO should have as well access to that information, because the distribution network is not infinite. We don't have infinite capacity. So many of the let's say the TSO, assuming that the distributed generation could generate whatever, but then you need to go in detail to each individual, checking if there are constraints or not. And then what is being discussed is how to get access to the information currently the TSO gets, to have that information in the DSO. But in all countries, I think there is a good connection between TSO, DSO. We have ICCP links, we have plenty of interfaces, so that should not be a problem.
Thank you.
Yeah, I agree with Juan Martí. I wouldn't use the word barriers. Of course, there are some things that we have to agree between TSO and DSO, and we have to coordinate. There is a big potential for distribution energy sources that can contribute to the balancing market of TSO, but the issue here is that the TSO cannot have observability of our assets. We have to be between the TSO and the distribution energy regulators in order to assure, to confirm that the activation of balancing services from sources connected to the network or our network don't create any issues in our networks. So there are issues like data handling that we have to agree, the coordination mechanism that we have between the TSO and the DSO. One barrier could be the technical barrier, that many resources are not don't have any communication yet. The smart meter rollout does not exist. Some issues that I have also mentioned in the presentation, for example, a harmonized interface for flexibility service providers, the data exchange standards that have to be more advanced, and standardization for flexibility market.
Thank you, Manoj. And going on flexibility point with the wind energy curtailment, Gerard, regarding this, are there also inverse mechanisms in preparation regarding the curtailment of generators to incentive loads in that area to consume temporarily?
Yeah, so I want to pick up on this one because we've actually just completed a trial this year on the very subject that you picked up in the question, Gunnar. We, in partnership with Octopus Energy, who are one of the suppliers in the UK, we've effectively requested a turn-up service, or the demand shift service from customers within the area at set time frames. So we actually got quite a good response. I think we initially had about 9,000 customers signed up, but probably 2,500 to 3,000 customers took part in each of 6 events that we scheduled. So from those, I think we had about 2.5 megawatts on average turn up during the windows that we asked for. So we were actually quite a successful trial with using an aggregator come supplier to provide that service. This is probably kind of first step. That was kind of timed. What I'd ultimately like to do is try and align things like the active network management so that we were informing when we ask for those services. So this was, for me, was almost kind of proving, can we get that service? But we've just recently completed a trial that outlines that there's definitely potential there to do so.
Thank you. And Tanya, I know that you already answered regarding the low voltage operation and smart metering, but this is still a very new topic for some countries that still don't have a smart metering rollout. So maybe I would like you to give here your opinion regarding this on the smart meeting reporting rate, if it's sufficient for a real-time operation.
Smart meter is true that it's mandatory in Spain, so we just use the data for everything we're able to. But probably if you are thinking about the state estimation, you have to think for sure not in every point at customer. Probably with only few sentinel smart meters or sensors, you can do state estimation using software or load flows, okay? So we are working as well because at the moment we are able to detect some failures at grid, but we are still not doing a massive state estimation or low voltage we are working on at the moment.
Thank you. So there's still a general question for everyone regarding monitoring solutions. What do you have in your companies? But maybe I will ask for you to answer this one offline, and I want to give maybe a general question from my side, following what Eva commented in one of the answers regarding what is coming next after Go4Flex. So which kind of report do you see from the work that you develop on this task force and the work that you started here on Go4Flex? What do you see that is needed to be done after this close work on grid observability, and as you see nowadays how things are regarding flexibility and integration of more distributed resources on the distribution grid, and the need of this being as much velocity as it can be from what we were doing before, let's say 1 year ago. Everything changed in 1 year, so the challenge for us DSOs, it's even more nowadays. So I would like to see from your side what you see that should be the next focus after this grid observability report. And maybe we can start with Eva.
Yeah, maybe not. Maybe not. We don't need another one. Flexibility Go4Flex reports, but I think for distribution system operators, there is a need to have, let's say, modeling for grid operation with a lot of distributed energy resources connected to the grid. However, yeah, this is not easy way to this is not easy to prepare such a common suited for all the DSOs from Europe model, but still it is I think due to a lot of distributed energy resources connected to our grid. This is I think emerging very interesting topic for DSOs.
Thank you, Eva. Juan?
Yes, I think we all of us, all the distribution utilities, we are seeing that the becoming a distribution system operator is coming. This report has helped us to understand the needs and how far or how close we are, but we need to be prepared. And this is in terms of tools and information, digitalization, and practices. So I mentioned that the two big areas or activities of the utility, which are operation and planning, needs to be reviewed, which this massive observability conditions, what can we expect from distributed energy resources, how to deal with this large amount of information. So we are seeing the roadmap. This is really the roadmap. So as soon as the idea or the target is to be prepared for the day that the regulations in the different countries move towards an open flexibility market, and I think that's the key. And in this sense, I think the report has achieved the target. So what is missing and what do we need to do? So we all have homework for the next years. Yeah.
I see. Thank you, Juan. So just maybe a small sentence from the rest of the speakers, and then we close the session. So Tanya, please, just a short note from your side. You're muted.
Well, I agree with Juan. Lot of challenges and work to do. We start to draw what is flexibility for DSOs, but we have a lot of work to step forward about automatization, software, and data. You know, so a lot of work to do. So we hope we still work together.
Thank you. Gerard, please.
Yeah, I think from my side, a lot of interesting learnings from the report. I would encourage where your local regulation allows, go out and try these things. Go out and you will learn more by doing than by hypothesizing. So if you can, if it's possible, get out there, try these things, work with your customers, find out what you can do, find out what's possible with automation and flexibility.
Thank you, Manolis.
Yes, I agree. We have to focus now on the implementation issues and to the lessons learned of what we have already implemented. So I generally agree with what Eva and Juan Martin said.
Thank you. It's yours. Are your turn?
Yeah, I think with this report, we have a good baseline of what currently the state of the art is, but things will become more clear in the future. So it's interesting to not lose each other and to see if dominant designs on specific parts of the solutions will occur, or maybe where European developments are that we all have to deal with.
Thank you. And now I give the word just to Eva and Juan, the leaders of this work, to the final closing marks.
Yeah, so thank you. But I think this question, these answers for the question, how do we see the future of our work is could be a closing remark, because you said a lot of interesting things, and all of us agree that now we have to try to implement and those solutions which are needed to achieve observability good enough in order to manage flexibility. And of course, we need to know how we understand flexibility at the level of DSOs. And because some of us could understand it in a different way. However, probably the same solutions we have to use in the future. So this is from my side as a closing remark. And what is more, I am very happy that we will be able to we are able to present our report, and maybe in the future we'll be able to present the new one. When do you have any words at the end?
Oh, yeah, it has been a pleasure to work with this task force, and I want to thank everyone and the contributors, and I want to thank Eva as well, because she has been the heart of this report, and I think we made a very, very good team. So hopefully to continue working in the future. So pleasure and thank you all.
Thank you, everyone, and thank you for being also here participating and giving words for discussion for these panelists. And if you still didn't read the report, you can download it here, and you can contact our panelists through email, and we will share the presentation and the recording of this session with all of you, so you can also assist later if you miss some part. Thank you all the panelists, and wish you all a nice afternoon.